Section 3.6, Factoring Polynomials. By the end of this lesson, you should be able to use the remainder theorem to determine the remainder of a quotient. Use factor theorem to factor polynomials of degree 3 or higher. Explain the limitations of factor theorem when factoring polynomials, and decipher when other methods of factoring are more suitable. So the first thing we're going to look at is remainder theorem, which states that if a polynomial, f at x, is divided by x minus a, then the remainder is equal to f at a. So we're going to see an example of that right there. Okay, so we have a polynomial here, and we're going to divide it by x plus 1, right? And then state the remainder. So because it's x plus 1, what I'm going to do is I'll probably decide to use synthetic division here. And the reason why I'm going to make that decision is because I see x plus 1 over here, and that's basically in the format of x minus k, right? Where k in this case is equal to negative 1. So let me set up my synthetic division right here. Okay. So I'll do my square bracket here. And then over here I'll put my negative 1. And then along the top I'm going to put my 1, my 4, my negative 1, my negative 16, and my negative 14. And then I go ahead and start my synthetic division. So I bring the 1 down, multiply by negative 1, I get that, right? And then I get, 3 when I add those together. Sorry, I'll just clean that up a little bit. So I get 3 right there. And then 3 times negative 1 is negative 3. So I end up with negative 4. Then I end up with 4 over here, and that yields negative 12. And then this would yield positive 12, and I have negative 2. So recall that when you have synthetic division, this right here is your remainder. Okay, so we can say, therefore, the remainder is negative 2. And what remainder theorem says? Well, if we evaluate the function at x is equal to negative 1, we should still come up with this remainder, right? So if we evaluate this polynomial function at x is equal to negative 1, well, it will return the remainder. And the reason for that is as follows. You will recall this equation, which is that the dividend is equal to the divisor times the quotient, then plus remainder. Okay, so if my dividend here is x to the power 4 plus 4x cubed minus x squared minus 16x minus 14, and that's equal to x plus 1 times some quotient, which I don't know, e plus remainder, which I know what it is, but let's just say that I don't know it right now. Okay, so effectively what they're saying is if we let x equal to negative 1, well, what will happen there is this will become 0. And as a result, this right here becomes 0, and you are left with the remainder, right? So what we're going to do is we are going to evaluate the function at negative 1, and that should just yield the remainder because that would cause this to become 0, leaving only your remainder. So negative 1 to the power of 4 plus 4 times negative 1 to the power of 3 minus negative 1 squared minus 16 times negative 1 minus 14. Okay, when we put in all those numbers, we get 1 minus 4 minus 1 plus 16 minus 14. And when we evaluate that, we get negative 2. So again, when we divide by x minus a, the remainder is equal to f at that a value. And we saw it over here, and we saw it using a remainder theorem. And so we just repeat that over here in this box, right? Same thing that we saw before. So let's just go ahead and use the remainder theorem as we see it right here. So in this case, this question asks us to determine the remainder, and they give you the function, and is divided by that factor x minus 1. So I don't need to go ahead and do synthetic division for this, because using remainder theorem, if I evaluate at x is equal to 1, I should be able to find my remainder, right? So I'm going to set x equal to 1, so that therefore f at 1, right, should equal the remainder. So there we go f at 1 is equal to 1 to the power of 4 minus 7 times 1 plus 2 times 1 squared plus 9 times 1. And I input all these values and I get 1 minus 7 plus 2 plus 9, and I end up with 5. And so what you'll find is that when you input the value that we see here, right, f at a, the remainder is returned. So therefore we go remainder is 5. And this is something that we saw previously in dividing polynomials, but this is going to help us with our factoring as well. And it helps us with factoring by seeing what we have on the next page right here. It says that factor theorem states that if you evaluate at f at a and there is no remainder, then x minus a is a factor of the polynomial. So we can look right here. It says, is x plus 1 a factor of this polynomial? Well, we can try dividing it, and if we divide it and the remainder is 0, then this is certainly a factor, right? And as we can see, this is in the format x minus k, so k is equal to -1. So what I can do is I can go ahead and set up my synthetic division and try to evaluate this. All right, so I can divide the polynomial by x plus 1. And so I'll set up 2, 3, 1, -14, and -14. So bring my 2 down, multiply by -1, I get -2. And then I get 1 right there, and then 1 times -1 is 1, and so this becomes 0. And then 0 times -1 is still 0, so I get -14, and then -14 times -1 is equal to +14, and I get 0. Okay, so as we can see, the remainder is 0. So 0 remainder, right? And then effectively we can see that therefore, right, if there's no remainder, then that means that 2x to the power of 4 plus 3x to the power of 3 plus x squared minus 14x minus 14 is equal to x plus 1 times, and then you just have to remember over here that this means 2x cubed plus x squared plus 0x minus 14. So then 2x cubed plus x squared minus 14 right there. Okay, so that was a lot of work just to find out that x plus 1 was in fact a factor, right? We'll just use the remainder theorem, and we will sub x is equal to -1 right here. Because if we sub x is equal to -1 into the function and it returns a remainder of 0, then we know that it's a factor. So if the question is not asking us to factor it, if it just wants to know whether or not it is a factor, then we can say, all right, let's do f at -1, is equal to 2 at negative 1 to the power 4 plus 3 negative 1 cubed plus negative 1 squared minus 14. Sorry, let me just clean that up a little bit. Minus 14 times negative 1 minus 14. And when we evaluate this, we get, effectively, we get 2 minus 3 plus 1 plus 14 minus 14. And that equals 0. So therefore, x plus 1 is a factor because when we input x is equal to negative 1 into the function, we get a remainder of 0 there. So therefore, x plus 1 is a factor since f at negative 1 returns a remainder of 0. Okay, and that is in fact our factor theorem. So, determine values of a that will produce a factor of the polynomial. So we can make our lives a little bit easier by taking our function right here and looking solely at the final term, negative 10, right? And that's if the leading coefficient of the polynomial is 1. And in this case, the leading coefficient of the polynomial is 1. Then we look at the integer factors of the last term. So let's take a look at the integer factors of the last term. Well, negative 10, the integer factors of negative 10 are, we're going to try x is equal to plus or minus 1. We can try x is equal to plus or minus 2. X is equal to plus or minus 5. And x is equal to plus or minus 10. Right? So let's try evaluating the function. We'll start with the easiest one, which is let's try evaluating the function at 1. And if it yields a value of 0, then x minus 1 is a factor of that polynomial. So if I input these values, I get 1 cubed plus 2 times 1 squared minus 3 times 1 minus 10, and I go to input that, and I get negative 10. Right, so negative 10 certainly is not equal to 0, so therefore I know that x minus 1 is not a factor. Now, I'm writing this out for you guys, but in the future you don't have to, you just have to do the calculation. If you find that it's not a factor, you don't have to write therefore x minus 1 is not a factor, you just move on to the next value. Right, let's try f at negative 1. Right, we're trying our most simple, our most simple values. So negative 1 to the power of 3 plus 2 times negative 1 squared minus 3 times negative 1 minus 10. Okay, and we go to evaluate that, and we end up with a value that is not going to be, we can see it's not going to be equal to 0. So we have negative 1 plus 2, so that's positive 1. Positive 1 plus 3 is 4. 4 minus 10 is equal to negative 6. As you can see, negative 6 does not equal to 0, so that means, therefore, x plus 1 is not a factor. So we'll try another one, and the next one we're going to try is f at 2. Okay, so that means 2 cubed plus 2 times 2 squared, then minus 3 times 2, minus 10. Lo and behold, we end up with 0. So therefore, x minus 2 is a factor. And once we know that x minus 2 is a factor and that will yield a remainder of 0, we can take our polynomial here and divide by x minus 2, and we can start to factor this down into simpler parts. All right? Now, here's the issue. In this function right here, we have a leading coefficient that is not equal to 1, it's equal to 3. And so what we have to do is we have to try factors of the final term divided by factors of the leading coefficient, okay? And so we can do, like, for example, we can do plus or minus 1. We could do plus or minus 3, right? We could also try plus or minus 5, right? Because 15 over 3 is equal to 5. And so we can try a whole bunch of these combinations. Now, here's the issue, is that we can take a look at doing all of this, like substituting 1 and substituting -1, positive 3, -5, and what you will find is that none of those factors result in a factor of the polynomial, right? So we find that f at 1 does not equal to 0. We try f at -1, that does not equal to 0. We try f at 3, that does not equal to 0, so on and so forth. So what I'm saying is, after we've tried all of these, none of these equal to 0. And therefore, that's a limitation of your factor theorem, right? Is that, okay, this cannot be factored simply, right? So I'll just put ... here, indicating that we've tried all the other possibilities. And so therefore, okay, f at x is equal to 3x cubed plus 7x squared minus 3x plus 15 cannot be factored using factor theorem. Okay, so if we want to find the factors of this, well, effectively we need to look at what values of x will cause this function to be 0, right? So if I'm looking for the values of x that will cause the function to be 0, effectively what I'm looking for here are x-intercepts. So what I might turn to in this case is I might turn to a graphical solution. I might plot this function and find where the x-intercepts are. So I'm just going to take a second and do that off camera. Okay, so what I've done here is I've plotted the function that we were going to try and factor using factor theorem into Desmos, and I looked at values of x that would cause the function to equal to 0, so effectively the x-intercepts. And as you can see, it doesn't come out pretty cleanly. I have this rational value of an x-intercept. So in this case, factor theorem is not always going to work, right? It doesn't always produce clean results. All right, in this next question, we're asked to sketch a graph of this quartic, and we're not given really any other information. We're just given this quartic. Well, one thing that I can see is it has a positive leading coefficient. It's a quartic, so it's going to be opening up. The first thing that I'm going to do is I look at all these terms. 4x to the power of 4, 6x to the power of 3, minus 6x to the power of 2, minus 4, and I might in fact choose to factor out both a 2 and an x from this. So I'm just going to simplify things. Okay, 2x, and then I would get 2x cubed plus 3x squared minus 3x minus 2. So I know right now that the function is going to pass through 0, and it's going to pass through 0 in a linear manner, right? But I have this cubic here, and I don't know what the zeros are for this cubic. So in order to find the zeros for this cubic, what I'm going to do is I'm going to see if I can factor this. So I'm going to find values of x that would cause this to return a remainder of 0, right? So I look at my last value here, -2, right? And for -2, I can think of all the possible factors of -2. So I can try x is equal to plus or minus 1 and plus or minus 2. So I'll try with the most simplest one, which is, let's try inserting x is equal to 1. All right, so then I get 2 to the power of, 2 times 1 to the power of 3, plus 3 times 1 to the power of 2, minus 3 times 1, minus 2. And I get 2 plus 3 minus 2. Well, that certainly equals 0, and that means that, therefore, x minus 1 is a factor of that cubic, right? So this cubic, x minus 1, is a factor. So what I'll do is I will then use synthetic division to factor this cubic. So 1, right? Because my k is equal to 1 right there. My k is equal to 1. And then I'm going to factor this cubic right here. So I write 2, 3, negative 3, negative 2. So I bring the 2 down. 1 times 2 is 2. I add that together. I get 5. 1 times 5 is 5. I add these together. I get 2. 1 times 2 is 2. And I add these together and I get 0, which is what I expected. I expected a remainder of 0 because x minus 1 is a factor of this cubic. And so I'll just have to remind myself that this means that this is 2x squared plus 5x plus 2. So we continue to factor. F of x is equal to 2x, and then I've now factored this cubic into x minus 1 and 2x squared plus 5x plus 2. Okay, this right here, this quadratic, 2x squared plus 5x plus 2, that can be factored further. So f of x is equal to 2x, x minus 1, and I can factor it further by thinking, okay, let's take a and c. 2 times 2 is 4. So I need two numbers that multiply to 4 and add to 5. Well, two numbers that multiply to 4 and add to 5 are positive 4 and positive 1. So then it's just a matter of splitting up the middle term. And then factor by grouping, right? So you set up brackets around here, set up brackets around here. And I'm not going to go through all the factor by grouping because that's something that you've done in previous years. And so you'd end up with 2x plus 1 and then x plus 2. Okay, so we have now a factored form of this quartic. And that factored form of the quartic is actually quite helpful because now we know where the zeros are. So we know that we have a 0 at 0, 0, right? So what I'll do is I'll scroll down here and I'll put, we have a 0 at 0, 0, okay? We also have a 0, let me scroll back up here. We also have a 0 at 1, so I have another 0 at 1, 0. And then we have a 0 at negative 1/2. Okay, so let's go right here. We'll say that's negative 1/2, 0. And then we also have a 0 at negative 2. Great. The final thing that we're going to do is we're going to find the y-intercept. Well, you should, by looking at this, you see, okay, well, we find the y-intercept by setting equal to 0, x equal to 0, right? So the y-intercept, we set x is equal to 0. But you'll notice that if x is equal to 0, then this entire function becomes equal to 0 because of this first factor right here, right? 2 times 0 is 0, and then 0 times anything else is equal to 0. So if you set x is equal to 0, therefore f at x, or y, is equal to 0 as well. So this right here represents our y-intercept. Now, we know that this has a positive leading coefficient, so it's going to open up. That tells us about our end behavior, right? And so I'm going to sketch now the graph of this function without looking at where the turning points are. The last thing that we need to know is that because all of these factors are linear, which means that they're raised to the power of 1, all of these, right? This is 2x to the power of 1, there's a 1 there, there's a 1 there, there's a 1 there. We're going to see linear behavior through all of those zeros. Okay, so I've sketched this out, not my best work, but for the purposes of this question, that's fine. Okay, finally, factor theorem should only be used as a last resort. Right? You've learned a lot of tools over the past few years to factor without it. So you can first of all try to factor out a common factor such as a number or a variable, then see if you could factor by grouping. Right here, find a common binomial factor. You might end up with a difference of squares, or you might end up with a trinomial that is perfect square trinomial. And if you have a quadratic, you can try using the discriminant, because if the discriminant is a perfect square, then it is in fact factorable. So what we're going to do here is we're going to factor this, right? And this is where a lot of students tend to go wrong, and they see a quartic like this and they immediately think that they have to use factor theorem, right? Well, you don't. That should be, again, your last resort. You need to try everything else first and then use factor theorem. So I can see that in each term of this quartic, I have an x value. So let me factor out an x. Then I get down to a cubic. Okay, and when I look at this cubic here, I'm actually able to factor by grouping. So I can do this. I can say x, and then I can go, let's say I take an x right here, an x squared out of this. So x squared, then I get x minus 6. And then I'm going to take a negative 4 out of these last two terms, negative 4, and then I would get x minus 6. Okay, so right here I talked about finding a common binomial factor. That's what this is. It's in common, it's a binomial, and it can be factored out. So x minus 6, x squared minus 4, and then we see over here, there we go, we have a difference of squares, x squared minus 4. So that's equal to x minus 6, and then x minus 2, x plus 2. Okay, so that is factoring without using any factor theorem. So again, please, when you get a quartic or a polynomial, see if you can use any of your previously learned tools to try factoring it first before you turn to factor theorem. This final question is a great example of a thinking question. So when 2x cubed minus mx squared plus nx minus 2 is divided by x plus 1, the remainder is negative 12. When you divide by x minus 2, you get a remainder of 0 because x minus 2 is a factor of this polynomial. So we're going to use remainder theorem and factor theorem to determine the values of m and n. So the first thing that I'm going to do is when I divide this polynomial by x plus 1, right, I get a remainder of negative 12. So that means I'm going to set x equal to negative 1, because if I substitute negative 1 into here, that will return my remainder. All right, so 2 times negative 1 cubed minus m negative 1 squared plus n negative 1 minus 2 is equal to negative 12. So here I end up with negative 2, then I end up with minus m minus n minus 2 is equal to negative 12. Okay, so I need to isolate my m and my n, so I get negative m minus n is equal to negative 12 plus 4. Negative m minus n is equal to negative 8. I'm going to factor out a negative here, so m plus n, and I've got my negative 8. Divide both sides by negative 1. Gets rid of my negative, gets rid of my negative there. So I get m plus n is equal to 8. The other thing that I can say is that n is equal to 8 minus m. Okay, so I can actually call this one right here equation 1. Right? I've only used this first piece of information right here. Now, if I have x minus 2 is a factor of that polynomial, if I set x is equal to 2, then this should return a remainder of 0 because it is a factor of the polynomial. So let's evaluate this. 2 times 2 to the power of 3 minus m 2 squared plus n times 2 minus 2, and that is equal to 0. So this is actually 2 to the power of 4, right? So that's 16 minus 4m plus 2n minus 2 is equal to 0. Okay. So I'm going to simplify this a little bit. I get 14 minus 4m plus 2n is equal to 0. Bringing the 14 to the other side, negative 4m plus 2n is equal to negative 14. Factoring out a negative 2 is equal to 2m minus n is equal to negative 14. Dividing both sides by negative 2. I end up with 2m minus n is equal to 7. And I'll call that equation 2. Now, we have two linear equations. So what we can do to find the values of the two variables, right, is I can sub one equation into the other. So I'm going to sub equation 1 into equation 2. Okay, so my first equation is n is equal to 8 minus m. So I'll take my n value, and instead of writing n, I'm going to write 8 minus m. 8 minus m, okay, and it is equal to 7, right? So what I did is I took the n right here, the 8 minus m, inserted it here, and that's equal to 7. So 2m minus 8 plus m is equal to 7. Okay, I'm going to bring the 8 over to the other side, and I'm going to add like terms. So the 2m plus m, 3m is equal to 15, m is equal to 5. So I've got the value of m, and then once you have m is equal to 5, you sub m equal to 5 into equation 1. Okay, and so n is equal to 8 minus 5, n is equal to 3. Okay, thanks for watching, and the homework is listed below.